So this session is on finite abelian groups. Okay, remember abelian group or a commutative group. For any two members of your group. Now, Barnard, he changes convention. Instead of using the capital letter G to stand for a group, he uses capital A if the group is abelian. Okay, so we'll use capital A for the rest of this session. So for any two members of A, AB equals BA, right? They commute. They can swap, and that's true for any two members of your abelian group. Abelian is the adjective of abel, A-B-E-L, A-B-E-L. That's the name of a Norwegian pure mathematician, early 1800s, and he's famous for proving that it's impossible to solve the quintic equation. Quadratic equations of this form, x squared plus ax plus b is naught, and the cubic with x dot 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 dot, and the quartic dot 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 dot. Now, people had found solutions to these in terms of the real numbers and plus and minus and divide and multiply signs and roots, square root, cube root, that kind of thing. So, encouraged by the success of finding formulas to know for the solution to x, people tried to do it for the fifth power, the quintic, and failed, and consistently failed, until people became suspicious that it was impossible to find a solution in terms of the basic arithmetic operations and nth roots. And it was Abel, in fact, who proved that it was impossible. So he's rather famous, Norwegian, and the Abel Prize is named after him, and that's now the equivalent of the Nobel Prize, but in mathematics. You can't call it a Nobel Prize because a mathematics prize was not in the will of Nobel. He just wasn't interested in math, so he didn't give one of his prizes to mathematicians. Okay, so abelian, the adjective, group of having this property for any two elements of the group A, is known as abelian, so based on the name Abel. Okay? Alright, now I'll introduce a new concept. Now, you're familiar with the concept of generator, generator. That's a generator G belonging to little g belonging to G, and that G can generate or create or make all possible elements of your group just by having powers of itself. So G to the naught, well, that's just E. G to the 1, well, that's just itself. G squared is, I don't know, some other element A, and G cubed is some other element B, and so on. G to the k minus 1, where k would be the order of the group, okay? Because this generator generates every element of the group. These are all the elements of your group here. Okay, so you're familiar with that. Now, in the context of abelian groups, A, you can have more, well, you can have what's called a generating set. So I'll write that down so you're familiar with the term. Generating set. And it's a set, so it consists of the elements A1, A2, dot dot dot, to A to the n, let's say. So we'll say there are n of them. And each of these is a different element in the set. So this is a subset. This generating set is a subset of big A. Okay. And the reason why it's called a generating set is that every element, so for all x belonging to A, x is of the form a to the 1 to the power r1 times a2 to power r2 dot 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 a to the n power r to the n. Okay? So in other words, you can, using these elements that belong to the generating set, which is a subset of A, you can create or generate every element, you know, for all element x belonging to A, that x is of this form. So by taking the product of the powers, now these are just integers, right? The powers of these elements of the generating set, so the product of the powers, okay, of this form, you can generate all of the elements. Okay? So that set there of these elements is called the generating set because you can generate every element. Similar in a way to the way the generator generates every element, but the generator is special because it's just one element. If you like, you can look on the generator here in the context of cyclic groups, because this group here of all these elements is the cyclic group. So you can look on the generating set as a generalization of the generator, or the other way around. The generator is a set of one member that is a generating set. So the generator is the set of the generator, put it this way. So here's the set with just one member, with G in it, the generator. That set is a special case of the generating set. Normally a generating set for an abelian group will have several members, right? And the generating set for a cyclic group just has one member. Okay? Alright, so now you may have too many members here. So if you throw one out, maybe you can still generate all your members of the group. But eventually you'll get to the point where you have now a minimum generating set. Okay? So minimal generating set. And what that means is it's the smallest number of elements here in your generating set, the smallest number of them, so that they are still capable of generating every member of your set. Okay? The minimal, like the smallest generating set. Alright, so we can start now. Well, perhaps I should give a bit of background. Why are we talking about finite abelian groups? Because we've reached the point, we're finishing off lecture 11. There are 19 lectures in this course, so we're right in the middle. And we already have quite a few tools and theory under our belts. So it's now possible to do something quite powerful. And so the next page or two in the text is a quasi-introduction to the classification of the finite abelian groups. Remember I was saying just in the previous session, to classify means make a list of all possible cases and then prove that list is complete, that there's no other case. That's it. Okay? So now we won't actually do that because it's pretty well M1, Master's first year level. But he does give a taste, and we now have enough tools to go a fair way down that road. Now, if you want to, if you're interested in group theory, then the next course I will be teaching on that topic will be at M1 level, and we will certainly do the classification of finite abelian groups. It's quite a large theory. All right, so let's start along that road. So let's do our first theorem. So this is theorem number 10 that works. Was it this one? I had a new one last time. Theorem 37. Oh, yeah, I think this is it. All right. Now on page 97 of your text, it's in two parts. All right. So let A be a finite group in which every element, other than the identity, I think I made a statement a lecture or two back, where I was saying that every element in a group was of order 2. Actually, that's not quite correct. There's always one exception. In every group, there's always one element that is of order, the element is of order 1, and that's the unit.